Howdy, folks. Michael with the Reason RX podcast here again, talking about engineering with the veteran engineer Hannes Hacker. Sorry, I need more food. Otherwise, I would have pronounced it right the first time. Sorry, Hannes. Could you introduce yourself?
No problem.
Say hi again.
Hello, my name's Hannes Hacker. As I said last time, I have just over 30 years of experience as an aerospace engineer, mainly in satellite engineering and operations. Leave it at that, or do you want me to go into
that's
more
good.
detail like last time?
They can look in the show notes. I'll put the bio and stuff in the show notes again.
There you go.
And they can look at last time.
Okay.
And then, so we're talking about engineering. Let's review that a little bit. And then start getting into some other questions and discussion. So what's engineering again? How did you describe it?
Basically being a maker or being an inventor.
Mm-hmm.
Starting with a knowledge of science, of how nature works, taking the raw materials of nature, and then turning it into some kind of good or product to benefit people. And that is a very diverse set of things. It could be a mechanical machine. It could be a very complex machine or system like an airplane. It can be a system of systems. If you can imagine having a satellite network, we have different satellites that are talking to each other, to the ground, various ground stations, control centers. All of this is a big integrated system of systems. A satellite alone is its own very complex machine and a control center and radio antennas on the satellites, on the ground.
I haven't thought about it like that before, but of course I'm not an engineer, so I'm in education. But interesting, yeah. So you could, it took some scientific discoveries to learn about chemistry, metals, rockets, and then once we did that, we could engineer rockets into space. Then you can engineer a satellite, engineer the software in it, but then you can engineer how the satellites communicate with each other, and then get some science and engineer a cell phone. Instead of just being some scientific investigation, scientific experiment, we can actually engineer a cell phone that works in that system, and then you engineer the whole system. The satellites communicating with each other, the phone communicating with the tower, communicating with the satellite, and transitioning from one to another. And so it took engineering to make the transition between like Wi-Fi and cellular network more smooth and efficient. I hadn't thought of that before. So that's what's going on?
Yes.
Huh, cool. Okay.
In a nutshell.
And then, one thing I read about recently too was interesting. An example, it occurred to me, was engineering. If we hadn't discussed it, I wouldn't have thought of it like this, but read an article about some people wanting to identify bears, individual bears. So what they did, instead of starting from scratch and trying to get everything to identify a bear, they looked at what's already been done. And they found there's something like an app that can facially identify dogs. And so they got that, and they just engineered it to work with the bear. And that was like so cool.
Yes.
To help scientific study as well. So that would be engineering. Getting that one thing, as you say, modifying it for bears instead.
Sure.
Cool.
That happens a lot.
Yeah.
It makes the task a lot easier if you find something like that and say, I'm just going to modify this for my purpose. From an engineering standpoint, that's easy now. Once you get into the business standpoint and intellectual property, that's where I don't have the expertise, right? I mean, there could be an issue where if you're taking somebody else's invention and just, where is legally the point where you've modified it enough that it's now it's and I don't even know the legal term for it, right? that's why a lot of times, it also tends to be you have an engineering department, but you've got to have the various other departments, like a legal department, to figure out various things, like what I just mentioned.
Right? Interesting. Yeah. Yeah. When is it like patent or whatever violation, and when is it not?
Yes, exactly. That's a common path. It's like when I was in school, for example, and we kind of segued off here, but a very common combination for an undergraduate degree before getting a law degree is to study engineering as an undergraduate and then get a law degree. And then those people tend to become patent attorneys.
Huh. Interesting.
Because and they could be very specialized. I mean, you could have an electrical engineering degree, for example, and then just do patent law regarding, say, electronic devices or things like that.
Now,
like medicine or law, engineering is also a field that can get very specialized.
Yeah. Have you thought much about how we develop the concept of engineering? What's the logical hierarchy from the evidence of the senses?
That's a good question. I haven't really thought about that much.
So we won't dig into it here then. But clearly, what?
At some point, I think. That's a good question. That's more of a history question. At what point did the amount of inventions that we humans have become so diverse and so numerous? You actually, you transitioned away from like the ancient Greeks or in the Renaissance. You had people who were both scientists and engineers, to then having people who just do the engineering. They'll take the scientific principles that are taught to them and then use them to invent things. I hadn't thought about that much. I mean, today we're already there. I mean, we've got some specialties. It's like medicine or other laws. You get very narrow little specialties, and then you get somebody who becomes an expert in that specialty. And if that happens long enough, you can, I will confess, it's like when it comes to controlling the attitude of a satellite or knowing its orbit or things like that, I know quite a bit. But if you were to then turn around and tell me to design an antenna, I wouldn't know the first thing. I would have to go back to square one.
I know someone you could talk to about that. Talk to Hans.
Exactly. Exactly. And you'll see that if you look at job openings, you tend to do your if you're job searching as an engineer, you tend to do your keyword search, right? And you'll see, okay, we need an antenna design engineer. Like, okay, well, that's somebody who very likely has either a physics degree like Hans does or an electrical engineering degree. And then, of course, they've actually, you come out of engineering school, and then essentially your first couple of years, you're essentially, for the most part, you're an apprentice of a sort, right? Like I said, my undergraduate degree in aerospace engineering had a lot of diverse subject matter, like aerodynamics, aerostructures, flight dynamics of aircraft and spacecraft, and but if I were to try to say I want to become some kind of a aerospace structural engineer, designing the actual structures of an airplane, that would be like me being right out of college again.
Makes sense. But just so folks know really quickly, we are not talking about Hans of Iceland and the Victor Hugo story. We are talking about Hans Schantz, who's been a prior guest on this podcast and who I'll talk to again in the future. But they can look him up there. But so it's interesting. Like each type or branch of engineering is very tied to the science it builds on, depends on. Very rigorous hierarchy there. But in general, the concept of engineering depends on the concept of science. Without that, it wouldn't exist.
Yeah, and both engineering and science would not exist without epistemology.
Mm-hmm. Yeah, logic.
And metaphysics. And logic, yes.
That's one thing missing in modern education. People think they take a physics course or know what physics is like, or I deal with that with some people. They think they have a PhD in some science, and so they know what science is, and it's like, no. That's like studying a dog and being good at dogs and then claiming you know what mammals are. But the fact that they say that shows they're missing logic. It's a simple issue of classification there. Knowing science is different than knowing your own field.
Right.
Then there's the issue of...
Correct me if I'm wrong.
What did you learn? How did you learn it? Sorry, go ahead. Sorry.
When I think of science, I think of it as a method of thinking, right? Not a conclusion.
Yeah, right.
It's very interesting to study, for example, Newton's laws of gravitation. Right? There was that step. Scientists around Isaac Newton's time knew. By this time, they understood that the Earth was orbiting the sun, the moon is orbiting the Earth, and things like that. But they didn't know why.
Yeah.
They just know that all these planets and moons and asteroids all tend to orbit mostly the sun. Okay, I mean, technically the moon is also in orbit around the sun, but they didn't know why. And what there's a story that Isaac Newton was sitting under a tree and he watched an apple fall from the tree to the ground. And he asked himself, could the same force that causes the apple to fall to the ground be the same thing that causes planets to orbit the sun, for example? Is that same force what's binding the planets to the sun? And of course it is. And then he did, that was a hypothesis, and then he tested it, and it turns out that explanation worked. It was the explanation of why. And to me, when I think of science, science is the field of trying to understand why. Not the rote knowledge of what that is known up to that point.
Yeah.
So.
Agreed. So I'd say with a more advanced definition of science, not the stuff you generally hear in the culture that's too influenced by Plato, or the nonsense of Thomas Kuhn or some of these others. Science, I would say, is the inductive, integrated understanding of the nature of things and their cause-effect relationships.
Okay.
That's how I define it. Properly speaking, understanding includes induction and integration, but since it's not generally known, I say those things as well. But in reading some philosophy, the best logical breakdown of understanding that I've read involves three things: knowing the essence of something, reducing the concept to the evidence of the senses, and integrating that concept with other causally relevant things. Essence, reduction, like the opposite of induction, and integration, connection. That's the three requirements for having understanding. And then, of course, with changes in connections and integration, there can be more or less understanding. But induction is essential to it. Then, it's interesting bringing up Newton like that. that brought to mind another example of engineering. Newton, great scientist, but it took John Harrison, the English clockmaker, to come up with a functional clock that could allow people to measure longitude. There's that great book by Devis Sabel, I think her name is, about that. Have you read that?
I've not.
Yeah. Heard about it though?
Yeah, they needed a clock that you had fairly accurate clocks, but they wouldn't work on a ship.
Yeah.
Right. A clock that uses a pendulum, like a grandfather clock or something like that, is not going to work on the rolling deck of a ship. And they needed to know what time of day it was fairly accurately in order to compute their longitude. Latitude's easy. You just use you just measure it. I'm trying to remember the name of the device that they would use, but they would just they'd basically shoot a star, and they would measure the angle between the horizon and the star or the North Star, and that gives you your latitude. But longitude, you needed to know what time it is, and they didn't. So there was always some kind of guess, and it wasn't very accurate then. You might want to say, okay, well, we've been on a certain heading for a certain amount of time, so based on that, I'm making this up as I go along. I don't really know what the actual method. I'm thinking, well, if I didn't have a clock and I wanted to try to figure this out, this is how I might try first cut at it. But then you have the problem of, you're at a certain heading, but you don't know what the currents are.
Mm-hmm.
Right? If you're going against the current, it might be slowing down, and you're under, or it might be drifting you to one side or another. Like I said, This is just me kind of making this up as I go along. There might have been other smarter methods to do that before they had the clock. All right.
But actually, I was reminded of the thing too in teaching an ACT class, maybe ACT class. There was actually one of the readings we went over in class from an actual official ACT test was an excerpt from that book, Longitude. So it's like, whoa, cool. I've read this. And they mentioned that, there was actually, because of miscalculations, the way they did it before, using the clock Harrison invented, the way they did it before, there are actually some major disasters, shipwrecks, people dying from the miscalculations. Then what Harrison had to do that not even Newton could figure out, because Newton wasn't a specialist in clocks, he got metals that expanded at different rates and offset each other. So the pendulum or whatever would maintain a constant length no matter what the temperature. Had to try to get rid of friction, because that's what they pointed out, in the article that reminded me from Longitude. There was the rolling of the ship, changes in temperature, changes in pressure, different things like that can affect the timekeeping device.
Okay, yes, because you had ships that would go all the way up almost to the North and South Pole, or they would be in the tropics. So they could be in freezing weather, or they could be in tropical swelter.
Yeah.
And the same clock had to work under both conditions.
Yeah. I think she said, too, it's interesting, around the equator, I think if I remember right, maybe 1 degree of longitude was 68 miles. I'd have to do the calculations in my head to see if that's right for the circumference of the Earth, but not going to do it right now. I'm hungry. My brain's not working too well. But 1 degree or something was 68 miles. And of course, as you go towards a pole on either side away from the equator, it decreases from 68 slowly to 0. So there's that issue too. We've gone 1 degree, but how far is that?
Yes.
So
how far that is in miles?
Yeah.
You throw another wrinkle in there. The Earth is not perfectly round.
Flat. Thank goodness the water is pretty flat. Around circular, spherical.
Relatively speaking,
yeah.
It's
But
I took and this is an example of how computers have improved since I was at UT. But there is an entire graduate level class on basically the Earth's gravitational model, because it's not uniform. In an undergraduate or high school physics class, they will teach you that, okay, well, we're going to model the Earth as a point, and what's the gravitational pull of the Earth going to be as you go away from it, and what distance in the inverse squared law. Well, it gets a lot more complex than that. And, you have to take into account, when you want to really, really have some incredibly accurate spacecraft navigation, you're talking about, you're accounting for the fact that the gravitational pull over, say, the Himalayas is different than it is over the middle of the Pacific Ocean.
Mm-hmm.
And weirdly enough, there's less gravitational pull over the Himalayas. You'd think they're closer, but they're granite, which is less dense than the basalt at the bottom of the Pacific.
Interesting.
So I actually took a seminar once on a project where they had a satellite. It was just covered with corner cube reflectors, and they shined lasers at it from the ground. And they needed to know the Earth's gravitational model so accurately to figure out where and how fast this thing was traveling that at that time you needed a Cray supercomputer to crunch the numbers.
Wow.
I could do the same gravity model with the laptop that's sitting next to me on my desk today. And the purpose of this experiment is they took into account everything they possibly could to get the speed, the velocity of the satellite down as accurately as possible. And the stations where they shined the lasers at the satellite, they basically put in the concrete, they poured it all the way down to bedrock. And they had some small velocity left over after it was a Doppler effect, thing, anywhere from 2 to 12 millimeters a year. That's continental drift.
Wow.
They were physically measuring continental drift. That was just that floored me when that's amazing.
Yeah,
people can do that.
And the gravity thing reminds me of something I think we shared on Facebook years and years, decades ago. I think you're aware of this. There's some military planes require such precise specifications that when they're being built, let's say they're building a plane in England, it has to be floated in liquid on a special platform that's flat, and they have to consider the gravitational force of the moon, literally, to make sure the specs are, they stay within specs, because the gravitational effect of the moon can even affect how the plane's built. That's amazing.
I don't remember that, but
I'll have to try to dig that up and put it in the show notes somewhere. But typing it out, make sure I remember. But yeah, so and another thing, since we've been talking, showing that engineering depends on science hierarchically. You must have the concept of science before you can ever get the concept of engineering. Why else do new sciences come into play? Until we got electricity and then electronics down, there could not be electronic engineering, or we have biomedical engineering now, only because we got the biomedical, and that depended upon uniting biology and chemistry.
Yeah. But a lot of the same thinking and methodology are shared. In science, you have a hypothesis, and then you make observations either in the field or in a lab, and you try to determine whether or not those observations match your hypothesis. And if they don't, then you have to discard or maybe change the hypothesis.
Mm-hmm.
Engineering is a lot of the same thing. Okay, we've got an airplane design here. We're not going to just fly it. We're going to test it. And you don't just put the plane together and I'll say, okay, let's go fly it. I mean, you crawl, walk, run. You know, it's like, okay, well, let's just see if we can get this thing to taxi down a runway before we even take off. You know, and you'll notice things that, oh, there's something that we can improve in the design, mm-hmm. and you make the improvement. You know, hopefully your basic knowledge is such that you don't have to make major improvements.
Mm-hmm.
But it still happens. You know, that's why, for example, the Wright brothers and Burt Rutan were very similar in that if they were ever like pressured to say, when is your design going to be ready? They would never answer that question.
Yeah.
Other than when we decide it's ready.
Yeah, it'll be ready when it's ready.
It'll be ready when it's ready. It's like nature does not conform itself to your schedule.
Or like Gandalf, I'm never late. A wizard is never late. The proper time to arrive is when the wizard arrives.
There you go.
Go ahead, sorry. But yeah.
There is something we went over last time. If you remember, I talked about failing to consider failure,
mm-hmm.
including human error. Just this Monday, European company was launching a rocket. This rocket's called a Vega. It got to the fourth stage, and then they lost the satellite payloads. It was a Spanish and an Italian satellite that were sharing the ride, and they lost them both. And they've now figured out why. In the fourth stage, any rocket has what's called a thrust vector control.
Mm-hmm.
The nozzles don't just sit there. They have to be able to gimbal around to keep the rocket on course.
Mm-hmm.
And basically, there were a couple of cables that were connected to the nozzle of this fourth stage that were connected reversed.
Huh.
So the flight computer would tell, by whatever technician put this thing together, probably months ago or weeks ago. And so the flight computer would tell the thruster to gimbal in one direction, and it would gimbal in the exact opposite direction.
Whoa.
So the engineer in me is asking, why was that possible to even get them reversed in the first place?
Yeah.
At the very least, you should have two different colors. In a big, and in the part of the instruction manual, make sure the red goes into the red and the blue goes into the blue. Or you could even have different shapes of connectors so that it's actually physically impossible to get the two of them reversed.
Yeah.
Right. So, usually it's good to have at least, especially in what's called engineering psychology or human factors engineering, to have multiple different methods for somebody to tell what a control does, for example. Here's a funny story I read some years ago. If you remember 3 Mile Island,
mm-hmm.
It's a long, ugly story about how the nuclear power industry was just so overregulated by the government. But their control centers very often had some of the poorest human factors design you could possibly imagine. And in one case, there were two controls that were basically a lever, and they did opposite things. I think one of them pulled out control rods, The other one put them back into the reactor. Bottom line, that is, if you pick the wrong one, you could have a catastrophic failure.
Wow.
And they looked and felt identical to each other.
Genius.
I'm sure there was a label, but it was just two levers.
Mm-hmm.
One of the technicians said, okay, he'd noticed, he probably worked in a bar. If you've ever been to a bar and you notice that all the beer taps are different shapes,
Yeah.
that's on purpose. That is so that a bartender can just tell what he's pouring by feel in poor lighting conditions. That's the round one. That's the one I want. That's the square one. That's the flat one.
Sure.
And so they put handles from beer taps on these two levers at 3 Mile Island.
Huh.
They thought for themselves, and they said, if we ever have to make this decision, we got to make sure that we're well trained. It's like, the round one is this one, the square one is that one.
Huh. Interesting.
Pull them out, again, it's a very simple little thing, but I would say that falls into the category of engineering, right?
Yeah. Then for the satellite thing too, Italian, Spanish satellite, it's like, why don't they have backup systems? Why don't they have a double check? Why isn't someone else verifying the work? Check, double check, triple check. That's bizarre.
It's not the first time I've heard of it happening.
As Santayana or whoever and some other people have said, those who don't learn history are doomed to repeat it.
They're doomed to repeat it. Yep.
But of course, some people learn it and still repeat it. Unfortunately. But cool. So, yeah, and that has a lot of implications that we talked about today. Engineering, engineering education, doing engineering, getting the concept, to have a good educational system, to get ready to be an engineer. You got to have that scientific foundation laid in. And then, of course, with engineering, we got to bring in the human factor and human needs. It takes a little more awareness of human values, human life, to know what matters, what we need. But, well, I think you got some things to do. I need to eat dinner before I do an 1.5 hour long SAT class. So, any last words for this episode, Hannes?
No. I've got a few things I need to do as well. Cool.
But yeah, I still got a lot more to talk about. Good and bad engineering, education and engineering. But this is a good step towards that. An important idea, where the concept of engineering comes from. But cool.
Yeah, and okay, I'll try to give some more thought to education and engineering education.
Cool.
And we could focus more on that next time.
Cool. Awesome. So Thanks. Appreciate it. Good discussion.
No problem.
Okay. You have a good day.
Yep. Okay. You too.
Thanks.